Deep neural networks routinely achieve state-of-the-art accuracy on complex speech and visual recognition tasks. In a matter of seconds, they can process millions of high-dimensional inputs and map them to correct outputs. But the high level of expressiveness that drives this success creates a mathematical trade-off. To solve complex problems, these networks learn solutions packed with uninterpretable and highly exploitable properties. In 2013, a team of researchers including Szegedy and Ilya Sutskever published a paper titled Intriguing Properties of Neural Networks. The findings documented in this text establish the mathematical framework used today to study adversarial machine learning. We are going to decode the two specific discoveries detailed in this research. To understand them, we have to acknowledge that the standard mental models engineers use to visualize how neural networks learn are often mathematically inaccurate. We will look at evidence that challenges the idea of neurons as discrete feature detectors and expose the geometric vulnerabilities hiding inside high-dimensional decision boundaries. Correcting these intuitions is the necessary starting point for anyone moving from treating adversarial examples as glitches to treating them as predictable geometric consequences. We start with a pervasive professional misconception, the assumption that a single distinct neuron recognizes a specific feature. In visual tasks, engineers often expect one node to fire exclusively for a cat's face or a car tire. This is known as the single unit interpretation. It relies on the idea that high-level neural network layers naturally decompose into easily readable individual feature detectors. The researchers tested this assumption by analyzing the highest layers of multiple trained networks to see how they organized information. They compared the performance of these individual high-level units against random combinations of other units to see if the single neurons held unique semantic value. In a high-dimensional space, a random linear combination is simply a random diagonal vector drawn right through the activation space, cutting across multiple axes. The researchers started by taking a set of dataset images and projecting them onto a single neuron axis. As expected, the images clustered, grouping by recognizable semantic features like square shapes or faces. But when they projected that exact same data onto the random diagonal vector, the resulting clusters were just as semantically consistent as the single neuron clusters. This result shows that the network has not localized a specific concept into one isolated node. Instead, the model operates on the paradigm of a semantic space. This means all semantic information is continuously distributed across the entire activation space of the network. The direction of the vector within the space carries the meaning, not the individual basis vectors. This shifts how we must inspect models. Searching for a bad neuron to debug a misclassification is often a mathematical dead end because the error is distributed. Analyzing deep learning models by isolating individual neurons provides a false sense of security, masking how the network truly organizes and processes information. Early machine learning practitioners generally assumed networks learn smooth, continuous mappings. The expectation was that if you have two nearly identical input images, the network would output nearly identical predictions. The second major discovery of the paper shows that deep neural networks actually learn input-output mappings that are highly discontinuous. When you zoom in to the micro level around a data point, that smooth boundary breaks down into jagged, extreme mathematical folds. These sharp edges create invisible vulnerabilities. A data point that sits safely in the correct classification region can be microscopically close to a steep drop-off into an incorrect classification. Attackers exploit this geometry by reversing the gradient. During normal training, we minimize prediction error. Here, we calculate how to maximize it. This equation shows how the perturbation is calculated. We maximize the prediction error to push the data point over that jagged edge, while keeping the change to the image, represented here by R, extremely small. That constraint variable ensures that the total change applied to the pixels remains below epsilon, a threshold that makes the alteration imperceptible to the human eye. The attacker calculates this specific and visible noise matrix and adds it to the input. The network then processes the image, and the mathematical shift forces it to confidently misclassify the object. This manipulated input is an adversarial example. To human perception, the original image and the adversarial example are identical. To the machine's perception, the data point has been moved across a jagged mathematical boundary. The assumption of mathematical smoothness meant many models were deployed without a realization of how fragile they were to targeted, microscopic noise. One might assume these adversarial examples are just local glitches, quirks of one specific model's training process. The researchers tested this by taking an adversarial image engineered to trick one network and feeding it into a completely different architecture. The second, entirely distinct network produced the exact same incorrect prediction. When they fed the image into a third network trained on a different subset of the original data, it returned the identical error again. This proves these perturbations are not a random artifact of how one specific model was trained. This phenomenon is known as cross-model generalization. The cause is that different models, even with different architectures, are learning the same fundamental blind spots in their high-dimensional spaces. This generalization creates a significant security challenge for real-world deployments. It allows an attacker to train their own local proxy model, calculate the precise mathematical perturbations, and use them to compromise a target system they have never accessed. Because these vulnerabilities generalize across architectures and datasets, securing a model requires changing how the network learns the data space, not just adding more training data. The release of this research in 2013 shifted the focus of the machine learning community from measuring only accuracy to measuring a model's geometric stability. The paper defined the foundational concepts we use today. Semantic features exist broadly across the activation space, rather than inside single units. Decision boundaries in deep neural networks are jagged and discontinuous at the micro level. And this geometric discontinuity is what allows adversarial attacks to generalize across different models and datasets. Understanding these mathematical vulnerabilities is the baseline knowledge required to defend systems against adversarial attacks. Robust models must be designed with these geometric blind spots in mind, rather than assuming accuracy implies safety. To see more breakdowns of foundational research in machine learning, follow Inside Engine. The same expressive power that allows deep learning to solve complex problems is exactly what introduces these microscopic and invisible vulnerabilities.